Welcome to the deep dive. Today, we're not dissecting a business trend or a cultural phenomenon. We are reviewing an absolute pillar of strategic planning.
It really feels less like a casual chat and much more like an executive briefing.
It does. We're cracking open the future of the single most strategic component in modern transportation, the automotive chip.
Indeed. What we have here is a highly detailed, almost consultancy-style research report. It's a true technology roadmap,
Right.
and it meticulously maps out the current technological status, identifies some pretty glaring gaps, and then sets these incredibly aggressive development goals for the industry all the way out to 2040.
So our mission for you, the well-informed learner, is to distill this just enormous volume of strategic data. We're talking hard quantified metrics here.
Oh, absolutely.
Everything from raw computing power measured in TOPS, that's tera operations per second, all the way down to these granular reliability stats measured in PPM or parts per million failure rates.
And the goal is to turn this, very technical blueprint into a clear, actionable picture of exactly where this critical technology is headed.
And why it matters to everyone, not just the engineers.
Right, because this document, it really transcends a simple commercial market analysis. The sources we're looking at frame these chips as the foundation for the entire automotive industry's transformation.
Bedrock.
The bedrock, exactly. For intelligence, for connectivity, and maybe most importantly, for ensuring national information security and supply chain autonomy. In this new era, the chip isn't just a component.
No.
It is the core element that's going to determine global competitiveness in the whole mobility sector.
And you can see that in the money. The scale of the financial commitment shows just how high the stakes are. Let's just ground this with some numbers because they're pretty incredible.
They are.
The global automotive chip market hit a staggering $64.1 billion in 2023. And this is not some mature, stable
Not
market.
at all. It's exploding.
It's projected to exceed $80 billion by 2025. This entire ecosystem is in this dramatic double-digit growth phase. We're talking over 10% annual growth between 2022 and 2025.
And even if you just focus on one major region, that market alone is expected to hit $21.6 billion by 2025.
That kind of growth, it just screams that the race for sophisticated silicon in cars is already well underway.
And what's so fascinating here, and this really introduces the central tension of our deep dive, is that despite this incredible growth and this massive internal investment, the report identifies systemic structural gaps compared to the established international leaders.
Right, this is the why behind the whole thing.
It is. This recognition of vulnerability is the foundational impulse driving the entire 2040 roadmap. We're talking about shortfalls, across the board, in core technology design, in advanced manufacturing, in the maturity of the whole ecosystem.
The ecosystem part is huge, things like certification and tool chains.
Exactly. And maybe most critically, a deficit in the sheer volume of high-end, specialized talent you need to actually execute this kind of rapid advancement plan.
Okay, so let's unpack this. This strategic blueprint is essentially a declaration of intent to bridge that systemic gap and achieve what you might call silicon sovereignty. So to really appreciate the scope of this race for autonomy, we have to first map out the universe of the automotive chip itself. What precisely are we even talking about when we say car-grade silicon?
That's the perfect place to start, because before we dive into the roadmap and the timelines, we have to define this exceptionally high standard, the thing that separates a car-grade chip from, say, the consumer chips in your smartphone.
It's a crucial distinction,
Right.
a non-negotiable one.
Absolutely. Automotive chips operate in these hostile, high-risk environments, and the standards aren't just light voluntary checks.
No, these are deeply rigorous mandatory certifications. They demand proven long-term reliability and proof of failure mitigation.
The standards are brutal by design. They have to adhere to reliability benchmarks like AEC-Q 100.
Which is the stress testing one.
Yes, that covers stress testing across extremes of temperature, humidity, vibration. It simulates years of abuse on the road. Then you have IATF 16949 for stringent quality management throughout production.
Okay.
But the most critical one for the modern intelligent vehicle is ISO 26262 for functional safety.
That ISO 26262 standard, that's the ultimate hurdle, isn't it?
It is. It's the framework that ensures the electrical and electronic systems in a car won't cause unintended risk. It mandates everything from the design process to the final product verification.
And that high bar, the goal of 0 defects over a 15-year lifespan, that is a massive technological, organizational, and regulatory hurdle for any new player.
A huge one. It often requires companies to validate performance using decades of historical data, which is something new entrants just don't have.
So if that's the standard, let's take an inventory of the car. The sources break the chip ecosystem down into 9 distinct functional categories. It's a lot at first glance, but it gives us the full lay of the land, starting with the brains of the basic operations.
That brings us to our first category, control chips, primarily microcontrollers or MCUs.
These are like the car's reflexes.
Exactly. They are the workhorses, executing millions of simple, real-time, safety-critical tasks. Things like controlling the windows, managing braking pressure, regulating engine timing.
Okay.
The sources subdivide these into regional controllers, powertrain, and chassis controllers, which are the really safety-critical ones that need the highest safety certification. And then endpoint control chips for all the various little motors and switches.
And then you have the chips that get all the headlines, the ones dealing with massive amounts of sensor data, computing chips, or SOC system on chips.
These are the conscious brain,
Mm.
the ones responsible for complex decision-making.
Mhm.
They're reserved for the high-power, data-intensive systems, like intelligent cockpits running graphics and infotainment, and most critically, advanced autonomous driving platforms.
And they come in a few different flavors.
Right. Key forms include ADAS SOCs for driver assistance, cockpit SOCs, and increasingly these really complex multi-domain fusion SOCs that consolidate management of multiple high-level functions, like combining ADAS and cockpit processing onto a single chip.
Next step, memory. You can't compute anything without quick access to data, which brings us to storage chips.
Right. This includes DRAM for fast volatile memory you need for immediate calculations, and various forms of non-volatile memory like EEPROM, NOR flash, and NAND flash for permanent storage of operating systems, calibration data, all that stuff.
And the sources say the usage isn't uniform across the car.
No, and that's a key distinction. The high-volume data systems like the cockpit and ADAS, they use massive amounts of DRAM and NAND flash. But the lower-volume, ultra-reliable, safety-critical systems like motor controllers, they often rely on EEPROM or NOR flash, things that can handle frequent writing cycles without degrading.
Got it. Then we get to the conversation layer, how the chips talk to each other and to the outside world. That's communication chips.
These chips facilitate both vehicle-to-everything, or V2X interaction, so talking to infrastructure or other cars, and also the high-speed internal vehicle network.
And that's divided into wired and wireless.
Yep. Wire chips include things like CAN, LIN, and increasingly, Ethernet PHYs and switches. And SerDes is a big one.
What's SerDes for?
It's essential for transporting high-resolution camera and display data at just tremendous speeds. On the wireless side, you've got the whole suite. 4G, 5G, V2X-specific chips, Bluetooth, UWB for things like digital keys, and of course GNSS for navigation.
The next set of categories seems to be focused squarely on the electric powertrain revolution, starting with power devices.
These are the muscles and arteries of an EV.
Mm.
They're crucial for electrification. They manage energy conversion, allowing the battery power to be converted into the right current and voltage to spin motors or recharge the battery efficiently. This includes IGBTs, which are established technology, the rapidly growing silicon carbide or SiC MOSFETs, and emerging gallium nitride or GaN devices.
And right after that, we have the systems that manage the electricity, the power supply chips.
Exactly. These handle the detailed power management and distribution. This includes your DC to DC converters to step voltage up or down, LDOs for extremely stable, low-noise power, PMICs, which are power management ICs for system-wide power sequencing.
So they're like the utility grid operators for the car.
That's a great way to put it.
Yeah.
And if the PMICs are the utility operators, then their partners, the driver chips, are the linemen connecting the power.
Okay.
Driver chips translate the weak, low-power logic signals coming from an MCU, or an SoC, into strong enough signals to drive high-power loads. Activating solenoids, switching on headlights, running high-power motors. Without them, the brain can tell the body to move, but the body can't hear the command.
It's so easy to just focus on the digital side of things, but we often overlook the analog world. Analog chips seem critical for signal integrity and precision.
They are the sensory nervous system. They manage the signal chain operational amplifiers, or op-amps, comparators, analog to digital converters. And there's a vital subcategory here, especially for EVs.
Which is?
The AFE, or cell sampling chips. These are absolutely crucial for the precision required in battery management systems, the BMS. They ensure you get an accurate measurement of voltage and temperature across, thousands of battery cells.
Finally, rounding out the 9, we have the eyes and ears of the vehicle, sensor chips.
These form the perception layer, allowing the car to understand its environment. They're broadly divided into environment sensors, so ultrasound, radar, LiDAR, image sensors, and then in-car sensors for things like temperature, magnetic fields, and MEMS.
And their accuracy and speed directly determine how safe an automated driving system is.
Directly. There's no room for error there.
The sheer number of components and acronyms is staggering. But the sources point to a major shift in philosophy that sort of explains this complexity. The industry is breaking that traditional vehicle parts chip supply chain.
They are. They're moving to establish a new collaboration where the vehicle requirements directly drive chip innovation. And the chip, in turn, enables high-efficiency vehicle development.
The report synthesizes this into a pretty powerful new mantra.
It does, and it really defines the entire future strategy. Software defines the vehicle, architecture defines the software, and chips define the architecture.
Wow.
It signifies the elevation of the chip from just a component to the core definitional element of the modern vehicle. And that makes silicon sovereignty the ultimate strategic objective.
But that philosophical shift is meaningless if the physical silicon isn't actually available and competitive. So now we hit the core tension, the 2023 reality check. We need to benchmark the current state against international leaders to really understand the magnitude of the challenge.
Exactly. This objective assessment of the gap across performance, reliability, and the underlying process tech is the bedrock of these aggressive 2040 targets. If you don't understand the depth of the current shortcomings, the roadmap just sounds like a fantasy.
Let's start with the workhorse MCUs, the control chip gaps. You mentioned functional safety standards earlier, ISO 26262, and the ASIL levels. Where is the industry falling short there?
It's a profound safety and trust gap. Functional safety, measured by ASIL, or Automotive Safety Integrity Level, shows that domestic chips mostly achieve ASIL B.
Which is fine for, what, body control, lower risk functions?
Exactly.
Yeah.
But international competitors, especially in critical powertrain and chassis controllers, we're talking things that control steering and braking, they routinely achieve ASIL D,
The highest level.
the highest, most stringent safety level required for failure mitigation. The sources explicitly note that domestically, ASIL AD products have not yet formally achieved mass production validation.
And achieving ASIL D, is that just a technical challenge, like better design, or is it an ecosystem problem? Does it require overhauling the whole certification process?
It's both, and that's what makes it so difficult. It demands zero tolerance for potential failures. It requires thousands of man-hours and just vast amounts of data to prove statistical reliability. It means the entire process, from concept to retirement, must meet the standard.
So even if you design the silicon perfectly, without that mature, internationally recognized certification infrastructure, it's not enough.
It's not.
Yeah.
And the gap isn't just safety, it's also about architectural dependence.
Right.
There's still a high dependence on foreign core IP, overwhelmingly the ARM Cortex-M series for MCUs,
Right.
and a corresponding lack of autonomous IP for essential functions like CAN-FD and Emacs for Ethernet.
So if you don't control the foundational IP, you don't really control the architecture.
You're always paying tribute. And you're always susceptible to supply chain shocks.
And the most stark metric here, the one that really jumps off the page, is reliability, that PPM number you mentioned.
Yes, reliability measured in parts per million, the failure rate. Domestically, the current metric is 5 to 10 ppm.
So 5 to 10 chips failing for every million produced.
Correct. Now contrast that with international leaders who are consistently below 1 ppm.
Wow, that's a 5 to 10 times difference in failure rate.
It is. And that level of unreliability translates directly into exponentially higher warranty costs, and massive potential for recalls, and, most importantly, eroded customer trust.
Okay, so moving from the nervous system to the brain, let's look at the computing and SO gaps, the intelligence divide. This is where raw performance comes into play, especially for L4 and L5 autonomous systems.
And here we see large architectural and process gaps. For foundational CPU power, domestic SOCATs achieve about 250,000 DMIPs. That's the measure of raw processing muscle.
And international chips.
Roughly twice that, around 600,000 DMIPs. That performance deficit limits how quickly the vehicle can process non-AI tasks, like the operating system functions and redundant safety checks.
And the AI compute power, the TOPS, that gap is even more dramatic, right?
Right.
That's what runs perception and prediction algorithms.
Absolutely. Domestic systems are reaching about 100 TOPS in dense AI computation. International leaders, often leveraging dedicated GPU or FPGA acceleration, think NVIDIA's Orin or Tesla's custom silicon. They're hitting around 600 TOPS.
So a six-fold gap in raw AI computational muscle.
It is.
But hold on, that 6x difference isn't just about speed, is it? It reflects two very different design philosophies. Domestic systems often use custom ASICs, while international leaders use more general-purpose GPUs. What are the strategic implications of that choice?
That's where it gets really interesting. A custom ASIC is incredibly efficient at its one specific task. If you know exactly what algorithm you want to run forever, an ASIC is fast and low power.
But it's rigid.
Extremely rigid. The moment you change your software architecture or you need to process a new type of sensor data, the ASIC is a bottleneck. The international approach using general-purpose accelerators like GPUs offers flexibility.
So they can evolve the software with over-the-air updates.
Rapidly. The domestic approach potentially trades that long-term software flexibility for immediate performance gains, which could create a major challenge for future L5 scalability.
And performance is only half the story. The ecosystem, the tool chain around the chip is the other half.
Yes, the sources highlight that foreign leaders have these mature, closed-loop data platforms covering the entire vertical stack, from cloud data training down to the edge hardware, the software, and all the necessary tool chains.
Whereas domestic enterprises are still in the developmental phase for that.
They are. And it makes it incredibly challenging to realize the complete intelligent driving data processing loops you need to continuously improve AI models.
Okay, next, let's look at storage and memory gaps. The manufacturing lag. This isn't just design, this is about industrial capability.
For DRAM, the gap is clearly defined by the manufacturing process node. Domestic manufacturing is typically in the 17 to 18 nanometer process generation.
And the rivals.
They're already aggressively scaling to around 12 nanometers. That generational lag means reduced density and higher power consumption. For NAND flash, domestic products are at 200-plus layers, but international leaders are pushing 300-plus layers.
So superior density and capacity. And the performance metrics show a clear speed deficit, too.
Definitely. DRAM performance domestically is at 4266 megabits per second. Internationally, it's 9600. More than a twofold bandwidth disparity.
Which is a huge bottleneck when L4 and L5 vehicles are ingesting gigabytes of sensor data every second.
The data just can't get to the CPU fast enough, which forces compromises in real-time processing and decision latency.
Let's shift to the foundation of electric mobility. Power devices. The IGBT, SAT, CC, GaN gaps. This is about efficiency, charging speed, and endurance.
Right. Domestic products lag in critical reliability parameters here.
Right.
The max operating temperature for SECA-C and IGBT devices is typically 175 degrees Celsius domestically. International leaders are pushing 200 degrees Celsius. That 25-degree difference is huge. It means less need for bulky cooling systems and better performance under heavy load.
And the endurance metric, the power cycling capability, that's vital for EV owners, isn't it?
It is the lifespan of the chip under stress. It determines how many times the device can withstand temperature fluctuations from acceleration, braking, fast charging. Domestically, it's around 100,000 cycles, over 150,000 cycles internationally. If the power modules wear out faster, the cost of ownership and the vehicle lifespan are directly impacted.
What about integration and efficiency? You mentioned stray inductance.
Stray inductance is the enemy of efficiency in power electronics. Domestic products are around 5 nanohenries versus 2.5 internationally. Lower inductance means superior packaging, less wasted energy, and that translates directly to better EV range and faster charging with less heat loss.
And the newest material on the block, gallium nitride, GaN.
Highly promising for even higher switching speeds and efficiencies. However, domestic exploration of GaN for the main drive system is nascent. The sources project that small batch verification might only start around 2030.
That's a long lead time.
It reflects the extremely cautious approach you have to take when validating brand new materials in safety-critical multi-hundred kilowatt power systems.
Our last category split is sensor and communication gaps. Here we see some local strengths, but also critical weaknesses.
Yes, there are interesting pockets of strength. Domestic companies hold an advantage in LiDAR modules, often due to aggressive cost optimization and manufacturing scale. And their image sensors are considered first-tier, achieving high dynamic ranges of 140 dB.
Which means they handle bright sun and dark tunnels equally well.
Exactly. But the foundational sensor gaps remain. For example, ultrasonic sensors for parking lack product variety. More critically, MEMS inertial sensors, crucial for when GPS is lost, show lower stability.
How much lower?
10 degrees per hour of drift versus 5 degrees per hour internationally. The autonomous car basically gets lost twice as fast. which is a significant safety risk.
For wired communication, there's a peculiar anomaly here, isn't there?
There is. Domestic SUDEs, the high-speed link for cameras, actually leads in maximum rate 16 gigabits per second compared to 13.6 internationally.
A clear, specific strength.
Right, suggesting targeted R&D success. However, the wider Ethernet PHY side lacks support for 10G base ET1, a critical high-speed standard.
And on the wireless side, it's about reliance on global standardization.
Exactly. Wireless communication standards are still largely reliant on international bodies. While proprietary standards are being developed, they currently only exist as group standards. They lack the universal acceptance needed for global scale and interoperability.
Okay, so that's the gap, a pretty significant one. So if we connect this deep and detailed analysis to the bigger strategic picture, what is the grand vision?
The vision laid out by the roadmap is an incredibly ambitious declaration of technological war, achieving global technological leadership by 2040. This is not about being second best. It's about defining the future pace of innovation.
That sounds like a Herculean task, given the 5 to 10x gaps we just discussed. Let's break down what global leadership looks like in concrete, quantified chip goals.
Okay. First, for foundational chips, so control, storage, analog, the goal is extreme reliability and safety. They have to achieve high reliability, stability at 150 degrees Celsius or higher.
And ASIL-D?
Universally reach ASIL-D and achieve an ultra-low consistency with a parts per million failure rate of less than 0.2 ppm overall.
Wait, 0.2 ppm. We're currently at 5 to 10 ppm domestically. That means they're targeting an improvement of 25 to 50 times the current reliability standard? That's not just engineering improvement.
No, that's a complete redefinition of manufacturing quality. It's the zero-defect aspiration made tangible.
Okay, what about the EV side? The low-carbon driving chips?
For power, driver, and power supply chips, the focus is on unprecedented efficiency and high-voltage capability. They aim to achieve international leading KPIs in reliability and cost, specifically supporting 800V and above vehicle platforms, all the way up to 1500V.
And finally, the high-performance core, the intelligent chips. This is about supporting true AI-driven autonomy.
The targets here are just staggering. These chips have to support end-to-end AI large models, reaching an AI compute capability of 2,000 TOPS or more in a power-efficient package.
5,000.
Communication has to hit 56 gigabits per second and above internally. And the overall goal is achieving international leading performance, which must include having the capability to independently define the chip architecture and developing proprietary IP.
So what does this all mean for the industry structure? The roadmap is driven by 4 massive industry shifts that dictate how chips have to fundamentally evolve to meet these goals.
Right. These 4 trends are the tectonic forces guiding the next 2 decades of R&D.
Trend number 1, rapid performance increase. This is driven by the complexity of L4 and L5 autonomy, requiring massive sensor fusion and new functions in the cockpit.
It means every component has to scale dramatically. MCUs need substantially higher operating frequency and far larger embedded memory. Storage has to jump from the gigabyte level today to the terabyte level.
And compute just needs stronger compute.
Relentlessly stronger compute, capable of handling everything from real-time data processing to massive over-the-air updates.
Trend number 2, increased integration. This is the physical outcome of centralized architectures, the essence of the software-defined vehicle. They want fewer, more powerful boxes.
Exactly. Chip solutions must integrate multifunctionality to reduce complexity, wiring, and cost. Control MCUs will integrate AI coprocessors directly on the die. Computing stands are moving heavily toward multi-core heterogeneous forms, combining CPU, GPU, ISP, NPU, DSP, everything onto one package.
And this integration trend relies heavily on advanced manufacturing techniques, specifically chiplet technology. What is a chiplet and why is it so crucial for this?
Think of chiplets as high-tech Lego blocks for silicon. Instead of manufacturing one massive complex chip that has a high chance of failure, and the larger the chip, the higher the failure rate, you manufacture smaller specialized dies, the chiplets, that are known to work perfectly.
And then you combine them.
You integrate them into a single package using advanced interconnections. This gives you superior manufacturing yields, the ability to mix and match different process nodes, and just a lot more flexibility. The roadmap sees this as absolutely essential.
The third trend addresses the fundamental laws of physics. High performance versus low power equilibrium. More computation means more heat, more power draw, which is the enemy of EV range.
This has to be tackled through relentless process optimization. Compute platforms will move towards shorter process nodes, targeting 5 nanometers and even 3 nanometers by 2040. Even standard MCUs need to migrate to 28 nanometers or below. It requires optimization across process, layout, and software to balance peak efficiency with aggressive thermal management.
And finally, the non-negotiable fourth trend, high security and reliability.
This is about achieving that zero-failure goal. For storage, it means implementing sophisticated hardware encryption and secure data destruction. For power devices, it means new materials and structures. And across all chips, there must be comprehensive diagnostic and protection mechanisms built in fail operational capabilities, reinforcing that focus on ASLD throughout the system.
Okay, so this entire long-term vision is broken down into 3 distinct, measurable 5-year phases. This gives them checkpoints to gauge progress.
Exactly. It's a structured approach to a very complex race.
Let's start with the immediate phase, the heavy lifting required right now. Phase 1, 2026 to 2030, focused on performance elevation and supply chain foundation.
The overall goal here is pragmatic. Establish a solid, domestically controlled foundation. Products have to reliably support L4 autonomous driving and highly integrated cockpit functions. On the EV side, chips must fully support the 800V to 1000V platforms.
And the supply chain goal is paramount.
Absolutely. Building a complete high-reliability supply chain that encompasses design, manufacturing, packaging, and proprietary IP.
What are the quantified metric targets that define success for this foundational phase?
By the end of 2030, the targets are: AI compute must exceed 1,000 TOPS. That's a 10-fold increase from today. MCU CPU power has to reach over 10,000 DMIPs. Wired communication rate needs to hit 36 gigabits per second. And flash storage capacity is targeted at 4 terabytes.
4 terabytes of storage by 2030 is already substantial. What does that capacity signify?
It signifies the transition from simply recording events to needing enough capacity to handle the vast amounts of log sensor data you need for autonomous driving training and regulatory compliance. It moves data logging from a diagnostic tool to a foundation for continuous machine learning.
And what are the key technical tasks that have to be accomplished to unlock this initial jump?
We must see the autonomous development of ASIL-D CPU cores for control chips. That is non-negotiable. On the manufacturing side, which is a huge bottleneck, the first breakthrough and scaled application of non-volatile embedded storage has to happen at the 40 or 28 nanometer node.
Okay, moving to the middle game. Phase 2, 2031 to 2035, focusing on technology autonomy and ecosystem maturation. This is where the industry tries to shift from chasing leaders to creating its own standards.
The goal elevates dramatically. We move from L4 to supporting L5 full autonomous driving, which means true AI large model integration. Low-carbon chips have to support the next generation of power platforms, 1200 to 1500 volts. And the overarching goal is establishing autonomous chip architecture and fully autonomous software and hardware ecosystems.
The metrics reflect this huge jump in capability, especially in data handling.
Yes, by 2035, AI compute must hit or exceed 2,000 TOPS. MCU CPU needs to double again to over 20,000 DMIPs. Wired communication leaps to 56 gigabits per second, and flash storage capacity doubles to an enormous 8 terabytes.
8 terabytes. To put that in perspective, that's enough onboard storage to hold years of operational sensor data. What are the key focus areas for R&D to achieve this?
Key technical tasks include the autonomous development of core IP for computing chips, minimizing reliance on foreign licenses. This phase also demands the mature application of chips based on the open RISC-V architecture. And manufacturing needs to advance further, breaking through to 28 or 22 nanometer embedded storage.
And finally, the end game, Phase 3, 2036 to 2040, aiming for global leadership and superintelligence.
The goal is crystal clear. Performance at world-advanced levels, supporting the leap from general AI to what they call super AI, or ASI. This means achieving safe, autonomous, sustainable driving via robust domestic technology and completing the industrial system, including proprietary IP and autonomous EDA tool chains.
And what are the peak metrics that define this state of global leadership?
MCU CPU has to hit over 40,000 DMIPs. AI compute stays at 2,000 plus TOPS, but the focus shifts heavily toward efficiency and quality, not just raw compute. But the most dramatic jump is in wired communication rate, which targets 112 gigabits per second.
112? That's astronomical.
It is the foundation for absolute redundancy and centralized processing. It removes any possibility of network latency causing system failures. And the sensor goal, 500 meters detection with sub-centimeter precision, moves the vehicle from reactive driving to true predictive anticipatory autonomy.
We've seen the grand strategy. Now let's zoom in on the specific technical battlegrounds, the areas that require not just investment, but fundamental scientific breakthroughs.
Right. We can now look at the specific, hard-won technical details that will define success across the most critical components.
Let's start with the heavy hitters, computing chips, the AI engine. The sheer computational load for L5 and these huge AI models is just staggering.
The roadmap for intelligent driving SOCs targets a mind-boggling 3,000 TOPS of AI compute by 2040 in the driving domain. And achieving this requires overcoming massive challenges in both physics and design.
What cutting-edge processes are needed for that kind of density and speed?
The required manufacturing process will be at the very limit of physical possibility, 5 nanometers or even 3 nanometers. This highlights the foundational reliance on advancing the entire semiconductor manufacturing base. The R&D focus is twofold. First, achieving ASIL-D safety for these highly complex ADAS SOCs. Second, mastering multi-core heterogeneous design and pioneering revolutionary architectures like near-memory computing or compute-in-memory (CIM).
Wait, near memory computing, that sounds like it's addressing the core bandwidth problem. What does that architecture solve?
It solves the memory wall. Today, the CPU is incredibly fast, but it spends most of its time just waiting for data to travel from the memory chips. CIM physically moves the processing unit closer to or even into the memory module itself.
So it crushes the bottleneck.
It drastically reduces the distance data has to travel, crushing the memory bandwidth bottleneck. It's a revolutionary architecture that is essential if these chips are going to handle the petabytes of sensor data required for L5 in real time.
And what are the final 2040 metrics for these peak SIL cells?
The final CPU performance goal is over 1,200K DMIPs. GPU power must exceed 10 TFLOPS. And crucially, that memory bandwidth bottleneck must be fundamentally solved, all while maintaining ASIL-D functional safety despite the massive complexity.
Next up, power devices, the efficiency driver. This is the power plant of the EV. The goal isn't just raw power, it's density, efficiency, and thermal stability.
The transition in voltage platforms is absolutely critical. The roadmap outlines a clear progression, full support for 800V to 1000V by 2030, moving to 1200V by 2035, and then pushing towards 1500V by 2040.
And silicon carbide, SiNO technology, is the backbone of that transition.
It is. The maximum junction temperature for side-only MOSFETs is targeted to reach 240 degrees Celsius by 2040, a huge leap from the 175 degrees today. This increased thermal tolerance means the device is more reliable and needs less cooling.
And the emerging GaN technology, what are its specific milestones?
By 2030, the goal is for GaN-HIM-T to increase maximum current output and reach a 1500-volt rated voltage. The key R&D tasks focus heavily on tackling reliability, improving its resilience to avalanche breakdown, power surges, short circuits, and developing advanced packaging to reduce that stray inductance we talked about.
Let's turn to analog chips, the signal integrity challenge. These are often forgotten, but they're critical for precision measurement.
They are the link between the messy, noisy real world and the clean digital world of the SEC. The sources detail a massive planned leap in accuracy for precision operational amplifiers. The domestic 2023 maximum offset voltage is plus or minus 35 microvolts. The target by 2040 is to reduce that to plus or minus 1 microvolt.
A 35-fold improvement in precision. I need some context here. Why does reducing noise by a few microvolts matter to you as a driver?
That tiny improvement is the difference between a perfectly smooth sensor reading and a vehicle that occasionally misreads data. Reducing that bias to near zero ensures the central computer is working with the most pristine data possible, preventing false warnings and maximizing safety margins.
And for the battery management system, the BMS, where failure can be catastrophic.
The AFE voltage sampling accuracy is the absolute key to maximizing battery life and safety. It needs to drop significantly from plus or minus 3 millivolts in 2023 toward international leading levels. That precision is what tells the car exactly how much charge is left in the battery.
Okay, our final spotlight is on the strategic architectural move, RISC-V chips, the open architecture strategy. Why is adopting this open ISA so strategically important?
It's explicitly framed as securing long-term technological autonomy and mitigating geopolitical risk. By using the open ISA, which is royalty-free and allows for deep customization, the industry aims to achieve reliable computational technology without reliance on proprietary foreign IP, specifically ARM.
It's about control.
It's a necessary move toward deep domestic control over the fundamental chip architecture.
What are the performance and ecosystem milestones needed to make RISC-V a real contender?
RISC-V architecture aims to reach performance levels comparable to high-end ARM processors by 2030, while simultaneously improving power efficiency by 30%. The ecosystem target is equally aggressive, rapidly expanding from at least 100 partners initially to at least 500 ecosystem partners by 2035.
And the ultimate goal for 2040?
RISC-V is projected to become one of the mainstream chip architectures in the automotive sector, with domestic enterprises playing a core leadership role in the ecosystem. It's about transforming it from an experiment into a foundational standard.
We've discussed the metrics and the design goals, but technical breakthroughs at the chip level are meaningless without addressing the fundamental constraints upstream in the supply chain.
Success hinges entirely on autonomous breakthroughs in what the report calls the four foundational pillars. These are the unseen constraints that determine whether a brilliant design remains a lab achievement or becomes a mass-produced product.
So what are they?
Achieving self-sufficiency in sophisticated EDA design tools, the software used to design the chips. Full control over vehicle-grade IP cores. Massive investment in key semiconductor equipment. And finally, control over the core raw materials, especially for new compounds like silicon and GaN.
So without solving that EDA problem, those 3-nanometer chips are just a fantasy, right?
Exactly. And that addresses the design side. If that's the lifeblood, the manufacturing process is the backbone. The sources provide a clear, quantifiable roadmap for embedded non-volatile memory, or ENVM, processes.
Which are critical for MCUs and driver chips.
Right. The timeline provides measurable checkpoints. By 2030, stable mass production using 40 or 28 nanometer ENVM tech. By 2035, a breakthrough in 28 or 22 nanometer. And finally, by 2040, a breakthrough in 22 or 16 nanometer ENVM. This progression is essential for shrinking size, increasing performance, and hitting that critical 0.2 ppm reliability target.
And that focus on manufacturing depth is necessary because the final pillar isn't about technology at all. It's about collaboration and certification.
The sources stress that final success is defined by ecosystem collaboration. The strategy calls for building a comprehensive, efficient, and authoritative standard testing and evaluation system. This means standardizing the certification process so ASIL-D can be achieved reliably and efficiently.
Which means everyone has to work together.
It necessitates deep, continuous collaboration between vehicle OEMs, parts suppliers, chip companies, and software developers. Breaking down these vertical silos is the only way to move these high-tech, safety-critical components from blueprint to billions of units in millions of cars.
So we've seen a strategic blueprint that lays out not just ambitious goals, but the hard quantified metrics, from DPS and TOPS to power cycle counts and microvolt tolerances that define a multi-decade path to global leadership in automotive silicon by 2040. This entire effort is focused on the difficult structural shift from reliance to autonomous innovation.
And that roadmap, it projects wired in-car communication speeds hitting an astonishing 112 gigabits per second by 2040. For context, many cars on the road today run on networks that are orders of magnitude slower. That 112 gigabit per second rate is faster than most residential internet connections you could subscribe to right now.
Wow.
So consider what that speed means for automotive architecture and ultimately for your safety and performance. When the internal network of a car runs that fast, that bandwidth is the literal physical foundation for a truly centralized, fully redundant, and super intelligent driving experience. It's what lets the car handle petabytes of real-time sensor data with zero latency. That speed is what enables the next generation of predictive mobility.
That is the technological scale of the future of the vehicle. We hope this deep dive provides you with essential context for understanding the future battleground of the automotive industry.